All right, so today is the last lecture in this course, though today is not the last day. So today we shall continue with computing real integrals. We will develop the theme that we started yesterday, and so I'll just call the title of today's lecture as further examples on evaluation of integrals. Integrals of the form r cos t comma sin t, where r is a rational function. Integrands involving branch points, that is integrands involving things like log z, etc. So far, the multivalued functions are not figured into this chapter of calculating integrals. So we shall look into that briefly. But I'll begin the lecture by writing down few more exercises on integrals involving rectangular contours and semicircular contours. This one and this one, the first two have to be done using a rectangular contour, and the last two have to be done using a semicircular contour. Here you will have to indent at the origin, and here there is no indentation, whereas for this one the semicircular contour will enclose two poles, and you have to find the residue at either of the two poles. So, all right. So, these are four further problems for you, and if you look at books like Copson or Kreyszig or Churchill, Gamelin, these books contain lots of examples of this kind. This is just what I am giving you is just a sampling. So, you could try your hand at few of those examples from Gamelin and Kreyszig and Churchill and other texts like Copson, MacRobert. Lots of books are there in complex analysis. I mean, there's this big list. I can go on writing down books on complex analysis. You can pick up some of these books and work out the examples. You can read through the solved examples, right? So the four exercises are show that integral minus infinity. Okay, it's all there. So good. Let's come back. All right. So once again, for these two things it is a rectangular contour, and for these two things it's a semicircular contour, right? Shall we proceed to the next one? All right. Finished writing? Come on, hurry up. Hurry up with this. So everybody will be getting these things in email, right? All of you are getting these slides in emails. If anyone is not getting them, please let me know, right? Right. And we will discuss that in the end of the class. Integrals of the form 0 to 2 pi r of cosine t comma sin t dt, where r is a rational function. Okay, so simple examples, let us understand the procedure through simple examples. So let us look at the example. Calculate integral 0 to 2 pi d theta upon a plus b cos theta, where a bigger than b bigger than 0. Just write the integral, don't write everything, because you are not going to get time to copy down all the slides. So I am going to just go on, right. So this is the integral that you are trying to calculate, I. Of course, I can write this integral as a plus b by 2 into cos theta can be written as e to the power I theta plus e to the power minus I theta upon 2. And then I can put z equal to e to the power I theta. If z equal to e to the power I theta, when theta runs from 0 to 2 pi, z runs along a unit circle traced counterclockwise, right. Z traces the unit circle counterclockwise. So where there is e to the power I theta, it's going to be z, e to the power minus I theta is 1 over z, and what is d theta? dz is I e to the power I theta d theta, or iz d theta, or d theta is dz upon iz. So the integral, which is 0 to 2 pi d theta by a plus b cos theta, turns out to be d theta is dz by iz 1 over a plus b by 2 into z plus 1 over z. This can be written as, after some algebra, it can be written as 2 upon I integral mod z equal to 1 dz upon b into z squared plus 1 plus 2 az, and I am pulling the b out for convenience. So, this becomes a nice polynomial with the monic polynomial. It is a quadratic polynomial, right. So, this quadratic polynomial will have now 2 roots, and you have to calculate this using the Cauchy formula. What is Cauchy's formula? Integral fz dz upon z minus a equal to 2 pi I times f of a, where if a is inside the simple closed curve, correct. If there are several poles, it will be 2 pi I times the sum of the residues at the poles which are lying inside. So, this is you have to calculate the poles of you have to look at the poles of this. So, let us write it down. So, the integral can be written as minus 2 I by b. That quadratic polynomial has been factored as z minus alpha into z minus beta, where alpha and beta are roots of z squared plus 1 plus 2 times b by a z equal to 1. What is the product of the roots? Product of the roots is 1. Now, I am leaving it to you to check that neither of the roots lie on the unit circle. Please check this, neither of them lie on the unit circle, and then both of them cannot be inside and both of them cannot be outside, because otherwise the product will not be 1. Mod A, mod alpha, mod beta is 1. So, both mod alpha and mod beta cannot be less than 1, and both mod alpha and mod beta cannot be greater than 1. So, one of them is inside and one of them is outside, correct. So, let us call the one that is inside as alpha. So, alpha is the root which is inside the unit circle. Then the integral is what? Minus 2 I by b integral fz dz upon z minus alpha, where your fz is this function, the analytic function. Beta is outside the circle, right. So, it will be minus 2 I by b into 2 pi I times f of alpha, this is 1 over alpha minus beta, correct. Now, what remains is to find out what is alpha minus beta, and you have got the value of the integral, correct. So, the integral is what? 4 pi. So, if you do the algebra, 2 I and 2 I is 4 minus 4 I squared. So, it is 4 pi by b into 1 over alpha minus beta. Now, the quadratic equation can be solved using the quadratic formula, and here displayed you find the 2 roots. It is a by b plus minus square root of a squared minus b squared. Remember, a is bigger than b, b is bigger than 0. Remember, a and b are real numbers. So, both roots are real. Both roots are real, and the product of the roots is 1, which is real. The sum of the roots is what? Minus b by a. So, the sum of the roots is negative, the product of the roots is positive, both roots are real. So, both are negative. You have 2 negative roots. You have 2 negative roots, one of them lies in the interval minus 1 to 1 and the other one lies outside, correct. And so, and so you see that the root beta, both are negative. Both are negative. So, one of them is lying in the interval minus 1 comma 0 and the other one has to be smaller than the one that is inside. So, the one that is inside is the larger root. So, which one am I going to take? Alpha is a by b plus root of a squared minus b squared upon b, and beta is a by b minus root of a squared minus b squared upon b. So, alpha minus beta is what? 2 root a squared minus b squared upon b. So, you put that value and you get the answer, correct, 2 pi upon root of a squared minus b squared, all right. Next example, one more example we can calculate, but I will not carry it to completion because we have carried the first example to completion. 0 to 2 pi d theta upon a squared plus 1 minus 2a cos theta, where a is real, a is bigger than 1. And we put again as usual z equal to e to the power I theta, d theta is dz upon iz, and then you have a squared plus 1, 2 cos theta is z plus 1 over z. Once again you can simplify the expression and you get a quadratic polynomial in the denominator. right. So, you get 1 over minus a I integral dz upon z squared plus 1 minus a squared plus 1 upon a z, correct. So, it is 1 over I upon a into integral dz upon z minus alpha into z minus beta. Once again alpha beta is 1. Once again you have to check that alpha and beta do not lie on the unit circle, right. And so, you do all these calculations and right, and so you get 2 pi I squared upon a 1 over alpha minus beta as before. Assume that alpha lies inside the unit circle, then it will be exactly the other one, 1 over alpha minus beta into 2 pi I. And so, now I leave it to you to compute alpha minus beta and finish the problem, all right. Now, recall that we have done this integral 0 to 2 pi d theta upon a squared cos squared theta plus b squared sin squared theta by integrating over an ellipse, correct. You integrated dz by z over the ellipse a cos theta plus I b sin theta, and we obtained this integral. Now, do the same problem, do the same integral by integrating over a circle. After all, this is also a rational function, no? Cos squared theta, sin squared theta, right? Sin theta is 1 over 2 I e to the power I theta minus e to the power minus I theta, right? Cos theta is 1/2 of e to the power I theta plus e to the power minus I theta. Put it here, obtain the rational function and finish the problem. Calculation will be more difficult, of course, slightly more difficult. It won't be so straightforward as integrating on an ellipse. But the problem shows that there are several ways of carrying out the integral, all of them using complex analysis, but the proper choice of the contour can considerably simplify your work. You choose the contour properly, your work will be much simplified, but I think you should do it by both ways and you should compare the relative difficulty of the two methods. And then try these two exercises: integral 0 to pi sin nx upon sin x the whole squared dx, integral 0 to pi by 2 sin 2nx into cot x dx. First of all, you have to write it as an integral from 0 to 2 pi because this is an even function. Is an even function. So, this integral will be from minus pi to pi, and then or you can go from minus pi to pi or 0 to 2 pi, does not make any difference, perfectly same. You can still, it does not have to go from 0 to 2 pi, it can go from minus pi to pi also, same technique will work. Z equal to e to the power I theta will work, alright. This is also an even function, so it will go from minus pi by 2 to pi by 2, and then you can convert it to an integral from minus pi to pi, right. So, these are two additional exercises for you, try them out. Is it clear how to integrate 0 to 2 pi r of cos t comma sin t dt, where r is a rational function, alright. So, now let me read the problem: integral 0 to pi sin nx upon sin x the whole square dx, and the next problem is integral 0 to pi by 2 sin 2nx into cot x dx. Integrals involving log x, x to the power a, etc. So, now once again the best thing would be to look at a simple example to understand how the procedure goes. This is a slightly involved problem, so you please pay attention and please give your full attention to this. So, what am I going to do? Which function am I going to take first of all? The first thing that comes to your mind is f of z equal to z to the power a minus 1 upon 1 plus z. Now, a is not an integer. So, how do I define z to the power a minus 1? X of a minus 1 log z. Now, I have to explain to you what is log z. Are you going to take the principal branch or some other branch, etc. So, now and second thing you have to understand is which contour are you going to choose. Remember, the integral goes from 0 to infinity. So, the contour must somehow go from 0 to infinity, correct. So, but it will not quite go from 0 to infinity. You take the contour to be slightly above the x axis, parallel to the x axis, but above the x axis. This L1 that you see is not along the real axis. L1 is slightly shifted above the real axis and L2 is slightly below the positive real axis, right, and it has to go in this direction because the integral is from 0 to infinity. If you had an integral from minus infinity to 0, then it will be the other way around. It will be the other way around. You see, this is a keyhole. This, what you see here, the contour has a shape of a keyhole. This is called the keyhole contour, right. So, now, this keyhole contour is sitting in which domain? It is sitting on the complex plane with the positive real axis removed, correct. The positive real axis has been cut out. So, the argument, so I am going to take log x equal to ln mod log z equal to ln mod z plus I times argument of z, where the argument will run from 0 to 2 pi. I cannot take the principal argument because the contour is sitting inside the complex plane cut along the positive real axis, right. So, the positive real axis is cut off and the contour lies in C minus the positive real axis. L1 and L2, the L1 and L2 in the picture tend to they approach the positive real axis as epsilon goes to 0. What is the epsilon? Epsilon is the radius of the little circle here and r is the radius of the big circle here, okay. So, the contour consists of 4 pieces L1, L2, gamma r and gamma epsilon, right. So, please remember the contour. And so, now let us look at L1. What is f of z dz along L1? It is going to be limit, when epsilon goes to 0, this is approaching the origin, this is approaching the real axis from above. What is your f of z? F of z is x of a minus 1 log z upon z plus 1. What is happening to log z as z approaches the positive real axis from above? You are going to get ln x plus, what is the argument? Argument converges to 0. So, it is simply ln x, and so this will simply be x to the power a minus 1 upon 1 plus x, where the x to the power a minus 1 is a real x to the power a minus 1. On the other hand, when z approaches the real axis from below, that is when z lies on L2 and when L2 approaches the real axis, what happens to log z? Log z approaches ln x plus 2 pi, argument is now 2 pi. Argument is now 2 pi when you approach the positive real axis from below, right. So, what is the limit? So, when you integrate f along L1, in the limit, what are you going to get as epsilon goes to 0? You are going to get 0 to r x to the power a minus 1 dx upon 1 plus x. Is that correct? Is that right? You are going to get x to the power a minus 1 upon 1 plus x from when you take the limit from above L1 approaches from the top, right. So, finally, not only should epsilon go to 0, r should also go to infinity. So, epsilon goes to 0, r goes to infinity. What are you going to get? Contribution from L1 will go to 0 to infinity x to the power a minus 1 dx upon 1 plus x, exactly as you need. Is that correct? Is this clear what is going on? Right. So, what is the contribution now from L2? L2 is what? L2 is here in the picture. L2 is from below. What is the story for L2 now? The story for L2 is along L2, right? Along L2, what are you going to get? Z is x minus I epsilon. It is slightly below the positive real axis. So, mod z will simply converge to x, arc z will converge to 2 pi. So, z to the power a minus 1, which is exp of a minus 1 log z, will converge to exp of a minus 1 ln x plus 2 pi I into a minus 1, correct? 2 pi I into a minus 1. What is that? So, f of z is what? F of z is z to the power a minus 1 by 1 plus z. That will converge as epsilon goes to 0 to ln x into a minus 1, ln of x to the power a minus 1, and the exponential function will kill the logarithm, and you are going to get x to the power a minus 1. But this extra piece is there, no, 2 pi I times a minus 1, exp of e to the power exp of 2 pi I into a minus 1. This extra factor you have picked up. A is not an integer, so this is not going to be 1. So, it is going to be the usual stuff, x to the power a minus 1 upon 1 plus x into e to the power 2 pi I. So, what happens to the integral? Integral along L2 fz dz as epsilon goes to 0, r goes to infinity, converges to minus, why the minus sign? Because L2 is going in the opposite direction, minus integral 0 to infinity x to the power a minus 1 upon 1 plus x e to the power 2 pi I a, which is minus e to the power 2 pi I a times the integral that you want. Is that clear? Minus e to the power 2 pi I a into capital I. So, what is the total? What is the total contribution from L1 and L2 together? 1 minus e to the power 2 pi I a into the integral that you want, correct? Finally, you are going to say, it is an exercise for you to check that limit as r tends to infinity, epsilon tends to 0 from the bigger circle goes to 0. Integral along the bigger circle goes to 0. Now, along the little circle, along the small circle, z is what? Epsilon e to the power I t. Z is epsilon e to the power I t. So, dz is going to be what? I epsilon e to the power I t dt. So, what is mod of z of a minus 1? Mod z of a mod of z to the power a minus 1 is epsilon to the power a minus 1. A is real, remember, a is a real number between 0 and 1. So, do that formula, exp of a minus 1 ln x plus I times argument. If you do all those things, you will get this, right. So, now when you put in all these things, what happens to the integral along gamma epsilon? It will be less than or equal to 0 to 2 pi epsilon to the power a minus 1 coming from this, and there is one more epsilon when you do the dz, I e to the power I t etc. disappear when you take the absolute value, and you have 1 over 1 plus z, and z is epsilon e to the power I t. So, mod of 1 plus z is greater than or equal to 1 minus mod z. What is 1 minus mod z? 1 minus epsilon. So, the reciprocal will be less than or equal to 1 minus epsilon. As epsilon goes to 0, remember a is a positive number, a is a positive number. So, this goes to 0. So, the contribution from gamma epsilon, the little circle goes to 0, yeah. T changes from, no, T starts from the above the real axis, and it will go below the real axis. It will be slightly, it will be on the order of epsilon. You can actually take it to, see, it's up to you to see where the things crush. See that circle that you have, that's also small, and the distance between L1 and L2, that's also entirely up to you. You can take it to be epsilon if you want, right. So, is it clear? Yeah. All right. So, the contribution from the little circle also goes to the, so contribution from the little circle goes to 0, contribution from the big circle goes to 0, contribution from L1 and L2 combined gives you 1 minus e to the power 2 pi I a into capital I. And so, integral over this contour is going to be what? L1 plus gamma r plus L2 plus gamma epsilon. integral of fz dz over this entire contour equal to 2 pi I times sum of the residues of the poles lying inside. Now, what is f of z? Z to the power a minus 1 upon 1 plus z. Z to the power a minus 1 is analytic in the complex plane with the real axis cut out. 1 over 1 plus z, it has a simple pole at minus 1. So, now there is one pole inside the contour, namely minus 1. So, now you have to calculate the residue of the f at minus 1. So, all in all you get finally what I just spelled out. The contribution from the two circles go to 0, the L1 and L2 combine in the limit to give you 1 minus e to the power 2 pi I a into I, and the whole thing is going to be equal to 2 pi I times the residue of f at minus 1. Now, let us go ahead and calculate the residue of f at minus 1. How do you calculate the residue of f at minus 1? It is a simple pole. So, you are going to multiply it by z plus 1, correct, and take the limit. When you multiply by z plus 1, only z to the power a minus 1 remains. You are going to get minus 1 to the power a minus 1. So, quietly apply the formula x of a minus 1 log minus 1. What is log minus 1? ln of absolute value of minus 1 plus I times argument of minus 1. Of course, the a minus 1 remains, correct. The first term goes to 0. First term is ln of mod minus 1, that is 0. What is argument of minus 1? Pi. So, it is x of a minus 1 I pi, correct. So, the residue has also been calculated. So, you get the integral I equal to 2 pi I times the residue divided by 1 minus e to the power 2 pi I a. In this particular thing, you will get e to the power a I pi, exponential addition theorem, e to the power a I pi into e to the power minus I pi. E to the power minus I pi is minus 1. So, that is how this has become this, and is 2 pi I times e to the power I pi a. Bring the I pi a in the denominator, you get 2 pi I upon e to the power I pi a minus e to the power minus I pi a. It is pi by sine pi a. Is that correct? So, this is we have done this example in complete detail, correct. So, let us go through one more example. Integrate or compute, rather I should say compute the integral 0 to infinity log x dx upon x squared plus 1. There is one trick and only one trick that you should understand. That is, do not take f of z to be log z upon z squared plus 1. You should do that first. You should first take log z upon z squared plus 1 and see what happens. Carry out the full thing, and you will realize that when you carry out the full integral, you are not going to get the integral that you want, you will get some other integral. Does not matter. I think you should carry out the full calculation just to convince yourself that log z upon z squared plus 1 will not work. What you should take, your experience will also tell you that you should take log z the whole squared upon z squared plus 1. Okay, let us take this same keyhole I am taking, because the integral is from 0 to infinity. Sometimes if I have a minus infinity to 0, then I have to take the keyhole facing in the opposite direction. So, take this keyhole contour. As usual, the contribution from L1 will give you the integral 0 to infinity log x the whole squared upon x squared plus 1. You will say this is not the integral that you want, but wait, hold on. What will be the contribution from L2? Contribution from L2 will be what? First of all, there is a minus sign. Why? Because the L2 is going the opposite direction. 0 to infinity. What is the value? What is f of z? F of z is log z the whole squared. But what is the value of the log z along L2? It is log x plus 2 pi I from below. That is why you get log x plus 2 pi I the whole squared upon x squared plus 1. So, when you add the contribution from L1 and L2, what happens is the log x squared disappears and the log x term remains. If you had started out with a log x log z upon z squared plus 1, the log x term will disappear and what will remain will be integral 0 to infinity dx upon 1 plus x squared. You will not get the integral that you want, you will get some other integral. You understand why you took the log z the whole squared? Okay. Now, what remains? You have to do two more things. So, integral of, so finally, integral contribution from L1 and L2 gives you the log x term plus this integral, you know the value of this integral. It is an exercise for you to show that the contribution from the two circles go to 0. Now, I am not going to carry it out in detail, we have done one instance and that should pretty much tell you how to do the other things, correct. You have to do this every time, you have to check this, right. So, now what does Cochise theorem give you? Cochise theorem tells you that the sum of the 4 pieces equals 2 pi I times the sum of the residues at the poles which are lying inside. What is the function f z again? It is log z the whole squared upon z squared plus 1 and the keyhole contour. How many poles does it contain? Both I and minus I are sitting inside, correct? Both I and minus I are sitting inside. So, you have to calculate both these residues, correct. So, how do you calculate the residue at I? The residue at I is what? Yeah, it says I is a simple pole, I is a simple pole. So, the residue at I is z minus I into f of z, limit as z tends to I, correct. So, you have to, and one z minus I cancels out, one z plus I remains. So, it will be 1 over 2 I into log I. What is log I now? Log absolute ln absolute I, which is 0 plus I times pi by 2. And for the minus I, it is going to be log minus I the whole square. So, what is log minus I? It will be ln absolute minus I, which is 0 plus I times argument of minus I. What is the argument of minus I? 3 by 2 pi, right. So, you have those things. So, now you can put in the various pieces and you can finish the calculation. So, the exercise for you would be to finish the calculation, correct. Finish the calculation. Some more exercises: compute integral 0 to infinity, compute integral 0 to infinity ln x dx upon x plus a into x plus b. Which function are you going to take? F of z equal to log z squared upon z plus a into z plus b. How many poles are there inside the contour? None. A and b are positive. So, 2 excuse me. So, minus a and minus b are both, minus a and minus b are both inside, right. A and b are positive. Okay, good. Next problem is calculate 0 to infinity ln x the whole square dx upon 1 plus x squared. What is the contour and what is the function? The contour is a keyhole facing right or the keyhole faces right or faces left? The keyhole should be facing right, right. And what is the function you are going to take? F z equal to log z cube, log z cube upon 1 plus z squared. What are the poles? How many poles are inside? 2. They are the roots of. The next problem is integrate log of z plus I upon x squared plus 1 along a semicircular contour and show that log of x squared plus 1 upon x squared plus 1 dx is pi log 2, pi log 2. Integrate log of z plus I upon x squared plus 1 along a semicircular contour and show that integral 0 to infinity log of x squared plus 1 dx upon x squared plus 1 equal to pi log 2. So, please try out these things. Next problem, show that integral 0 to infinity log x squared dx upon 1 plus x squared is pi cube upon 8. Show that integral 0 to infinity log x squared dx upon 1 plus x squared is pi cube upon 8. Which function are you going to take? F z equal to log x cube upon 1 plus log z cube upon 1 plus z squared, correct? Keyhole contour with 2 poles inside, right? All right. Now, let us get to the next part of this whole thing. We will now look at an example of computing sums. We will now look at an example where we evaluate an infinite series. How to calculate sum of an infinite series using residue calculus. I will just do one example, that is all, just for illustration. You can look at the standard books, Churchill and other things, to get lots of other examples, right. So, let us look at the example of evaluating sums. Integrate pi cot pi z upon u plus z the whole squared over the rhombus with vertices r, ir, minus r, minus ir, r, ir, minus r, minus ir. Along that rhombus, you integrate pi cot pi z upon u plus z the whole squared, correct. Now, what are, and u is not equal to 0 plus minus 1, u avoids the integers, and u is a fixed number. U is a fixed number which is not an integer, that is all. And show that pi squared upon sin squared pi u is sum n from minus infinity to infinity 1 over u plus n the whole square. So, the function, what is the function? Pi cot pi z upon u plus z the whole squared. Please tell me what are the poles of this function pi cot pi z upon u plus z the whole squared. What are the poles of cot pi z? 0, plus minus 1, plus minus 2, plus minus 3, etc. They are all simple poles, and there is one more pole, right, minus u, which is a double pole, right, and that is why u is not an integer. Otherwise, this will interfere with the other poles and make it a triple pole. We do not want that. So, u minus u is a double pole, and there is a simple pole at the integers. Okay. So, the poles are all written here, right. Minus u is a double pole, 0 plus minus 1 plus minus 2, etc. Let us calculate the residues at various poles. What is the residue at a double pole? Remember the formula? When a pole of order k, you have to differentiate it to power k minus 1. You have to differentiate it k minus 1 times and then put. So, here we are differentiating d dz of z plus u the whole squared f of z, right. Z plus u the whole squared means it will simply be pi cot pi z. When you differentiate pi cot pi z, you are going to get pi squared into minus cosecant squared pi u, correct. That is what you are going to get. You have to put z equal to minus u, no. So, what you are getting is minus pi squared by sin squared pi u. This is nothing but pi squared by minus pi squared by sin squared pi u. And then what are the residues at the integer points? Integers are simple poles. So, you have to multiply by z minus n and you have to pass to the limit as z tends to n. The limit of a product, there are two things, limit of pi by u plus z the whole square will be pi by u plus n the whole square. And what is the limit of this? It is the limit of z minus n upon tan pi z, right. So, it is limit, so it will be pi by, this comes out, no, pi by n plus u the whole squared into limit of as z tends to n, z minus n upon tan pi z, correct. What is that? Use the L'Hopital's rule and you get pi secant squared pi z and z is equal to z, put z equal to n, you are going to get u plus n the whole squared. So, what is the sum of the residues of the poles within the rhombus? Rhombus is r I r minus I r and take r to be n plus half. Remember, it is a pi cot pi z. The rhombus should not pass through any of the poles. So, I have to avoid the integers. So, I take integer plus half. I take a integer plus half. So, the rhombus is a large rhombus n plus half, correct, n plus half, r is n plus half. And so, how many poles are there? From minus n all the way up to n, isn't it, and minus u of course. So, what is the sum of the residues of the poles within the rhombus? It is k from minus n to n 1 over u plus k the whole squared. They are the residues at the integer points and the residue at the double pole, which is minus pi squared by sine squared pi u. This will be equal to 1 over 2 or 2 pi I times this will be equal to the integral along the rhombus, right, or multiply by 2 pi I and this will be equal to 2 pi I times, sorry, 1 over 2 pi I times the integral along the rhombus. So, now if gamma is the rhombus, then 1 over 2 pi I times the integral of f z dz over gamma equal to this minus this, correct, that minus that. So, what do you get? You get this equation and now what I am going to do? I am going to allow the n to go to infinity and the rhombus becomes larger and larger. Now, you have to check as an exercise that cot pi z is bounded along the 4 sides of the rhombus. You have to write down the formula for cot pi z in terms of cos pi z upon sin pi z. Write down the equation of the line segment. Z is a point on that line. Put down the value and check that cot pi z is bounded. And then you have to show further that limit as n tends to infinity, integral gamma f z dz is 0, because the f z is bounded, correct. Now, dz, when you integrate along the rhombus, not f z, excuse me, cot pi z is bounded. You have in the denominator one more thing, no, z plus u the whole squared, and z is varying along the rhombus. So, the distance of z from the origin will be what? It will be quite large. The rhombus has side, see that r, what is that r? N plus half, correct. R is what? N plus half. So, that distance will be something like n upon root 2. The distance as z is running along the rhombus, the distance of z from the origin will be something like n upon root 2. Root 2 is an innocent constant. So, the distance is like, the distance of z is like n, but that z is appearing in the denominator, 1 over z plus u the whole squared. So, that particular business 1 over z plus u the whole squared is going to behave like 1 over n squared. That is going to behave like 1 over n squared. Now, what about dz? How do you calculate dz? You have to parameterize, no? When you parameterize, you are getting an r and an ir. R and an IR. How will you parameterize the line segment joining R and IR? TR plus 1 minus T IR, correct? Line segment joining 2 points where T runs from 0 to 1. So, what will be dz? Dz will be something like R into dt, no? Something like R times dt, and T runs from 0 to 1. So, you have an R in the numerator. What is R? N plus half. You have an n plus half upstairs and you have a n squared type business downstairs, and the T is running from 0 to 1. So, what will be the contribution to the integral? And the cot pi z is bounded, m, call the bound m. So, what will happen? You will get this integral fz dz, integral fz dz over gamma limit as n tends to infinity is 0. So, this I have already sketched how to go about this job. You have to carry out the details. Okay. So, now look at this equation. In this equation, you allow the n to go to infinity. This will, left hand side will go to 0. Right hand side you have a constant pi squared by sine squared pi squared, constant as far as n is concerned, and this will go, and what will be the limit of this as n tends to infinity? K from minus infinity to plus infinity 1 over u plus k the whole squared. So, you get finally the formula pi squared by sine squared pi u equal to integral sum minus infinity to infinity 1 over u plus n the whole squared. This is what you get. This is exactly the partial fractions expansion for 1 over sine squared pi u. See, just as when you have a polynomial, suppose I have 1 over pz, if pz were a polynomial, then you can write the partial fractions decomposition, right? But here you do not have a polynomial, you have an entire function. When you have a ratio of two entire functions, you are asking for a partial fractions decomposition. So, this is some kind of a partial fractions decomposition for pi squared by sine squared pi u. Now, in particular, the n equal to 0 term here is very interesting. It is 1 over u squared. So, pull the 1 over u squared on the left hand side and you write it as summation n from minus infinity to plus infinity 1 over u plus n the whole squared, n not equal to 0. Calculate the limit as u tends to 0 on both sides. So, I calculate limit as u tends to 0, pi squared by sine squared pi u minus 1 over u squared. Right hand side is simply twice sigma n from 1 to infinity 1 over u squared. So, here is an exercise, calculate this limit on the left hand side and find the value of sigma 1 over n squared. You can keep on doing this, you can differentiate this 2 times. You can differentiate this equation 2 times and you can calculate sigma n from 1 to infinity 1 over n to the power 4. You can differentiate this 4 times, you can calculate sigma 1 over n to the power 6 n from 1 to infinity, etc. You could of course differentiate it once and try to calculate sigma 1 over n cube, but you will fail. Nobody has succeeded in calculating sigma 1 over n cube in closed form. Sigma 1 over n squared is pi squared by 6. Sigma 1 over n to the power 4 is pi to the power 4 by 90. But sigma 1 over n cube has not so far been done. It's closed form calculation by every possible method seems to lead to some equation like 0 equal to 0 or something like that. You don't get it. Right? The odd ones and the even ones they cancel out. No, n from minus infinity to infinity. So, all the odd terms and all the even terms will cancel out. You will get 0 equal to 0. If you differentiate it even number of times, you will get the results. Correct? So, with this particular thing, I close the chapter, end of chapter 7, and it's also the end of the course. And here are some further references if you want. Everybody knows, I think, Churchill Brown. Gamlin, many people have bought a copy of Gamlin. E.T. Copson is a very old book. I'm sure many libraries will have it. Almost any old library will have a copy of E.T. Copson's book. And recently there is a book called Ablowitz and Focas, Complex Variables. That was published by Cambridge University Press. It's available in Indian edition. Though it may be difficult to find a copy because the copies may have been sold out. But you could try to get yourself a copy of Ablowitz and Focas. These are just 4 of the references. There are several references. I can go on giving you several slides consisting of references for complex analysis. There is no end to it. There is a book by Hovey. There is a book by Titchmarsh. Old books are Titchmarsh, Whittaker and Watson, MacRobert. Number of books are available. And then recently there is a book by Stallings. All sorts of, there are books, libraries are filled with books on complex function theory. Okay. So I think I'll close this session here, and this with this I declare this course has formally ended. Thank you very much for listening to me patiently and putting up with my pestilence.